We're going to get started. We're a little bit late. I would like to welcome you to the first lecture of the 2019-20 Presidential Lecture Series in a new building, celebrating TAMIU's 50th anniversary. I am Dr. Catherine Whiteman, Dean of University College, who presides over this lecture series. Before I introduce Dr. Arenas, TAMIU's president, who will introduce our guest speaker, I have a few reminders. Please put all cell phones on silence or vibrate and away from view. All other electronic devices need to be put away as well. Please be respectful of those around you who want to listen and pay attention to tonight's speaker by refraining from having sidebar conversations. If you need to take notes, we're going to ask that you take them the old-fashioned way with paper, pen, pencil. Most importantly, please stay until after the Q&A. We want to respect our guest speaker by remaining until the conclusion, which is after that point in time. Please remember that students will need to sign out after the Q&A in order to receive course credit. And lastly, we ask that you complete the evaluation forms. It's my pleasure now to introduce Dr. Arenas.
I can probably do this without having to use the microphone. Can you hear me back there? It's with great pleasure that I get to introduce this evening's presidential lecturer and the presidential lecturer. You have his bio on here. A couple of things I'd like to point out. He's very well published. He has had, almost throughout his whole career, he has been funded by both national and international agencies. And I think one of the more interesting things, and he'll talk about this, I know, this evening, he's had over 150 undergraduate students from both his lab and the MARC program go on to get PhDs. That's quite an accomplishment, and almost all of those 150 plus individuals are underrepresented minorities. I've known Dr. Panel for a long time. Not as long as my wife, but for a very long time. I think about 35 years I think I've known him. We interacted almost from the minute I walked onto campus at University of Texas El Paso. I was there for 24 years. He used to give me a bad time about going over to the dark side, becoming an administrator, rather than staying in the lab. I keep telling him, well, it's almost the same, because you deal with similar problems. That you do a set of experiments or you set up a hypothesis, and you do a set of experiments. You may not know for 8 or 10 years whether your hypothesis is correct, and that's the same thing in administration. We set up policies and procedures, and look for and do visions, and we may not know for 15 or 20 years whether what we want to do works out. But I will say that Dr. Panel is an outstanding administrator himself, because he took a fledgling program, the MARC program at the University of Texas El Paso, and made it one of the premier MARC programs in the United States. They've been recognized by the federal government. They've been recognized nationally. He goes around the country talking about MARC programs and how to develop MARC programs, and that is along with his research. And so he runs programs. He does research. He's in the lab day and night. He used to be in the lab day and night. He may not be now. So it's with great pleasure that I introduce this evening's speaker, Dr. Keith Panel.
So I will switch this on. And now, can you hear me at the back?
Yes.
Excellent, thank you. Thank you very much, Professor Arenas, President Arenas, sorry. I'm not used to, I give lots of talks, lots and lots of talks, all over the place. I just came back from 3 weeks in Japan, before that 2 weeks in Russia, and before that a week in England. I wasn't talking about the MARC program over there because they wouldn't quite understand what it's all about, which is in fact one of the great strengths of North American education at the moment, that there is an understanding that science isn't just done by old white guys like me, or even younger whitish guys like Dr. Arenas, but in fact it should be done by everybody, no matter where you've come from ethnically, economically, geographically. And as I'm going to point out, this is an international operation, that is science. And in America, we recognize that. I say we, I'm both an Englishman, well, I'm always an Englishman, but I'm also a US citizen, so I can say the we wherever I choose to say it, here or in England. So the bottom line to that is that this country has recognized that there needs to be a program at the grassroots to let and encourage all students, no matter background, as long as they've got talent, to move into scientific research. You wouldn't find programs like this so much in Australia, England, Germany. It just doesn't cross their mind. But the multi-diversity of this country, and some people will argue that this is a problem for America. Believe me, it is not. Anyone who thinks that the immigration into this country is inappropriate or wrong is themselves dead wrong. And I'm going to show you some stories to reinforce that particular notion today. So anyway, that's the University of Texas at El Paso. We just celebrated our 100th year a few years ago, so that's our what we call the Centennial Plaza. Is that the one? Okay, well, the green on green, but that's it. Right in the middle of the campus. It's a relatively new facility. It's a wonderful facility. It's a beautiful campus, and all you've got to do is go online, and it's got all this crazy architecture that comes from Bhutan. And this is an international university. So anybody here from Bhutan? I didn't think there would be. Anybody here give me 2 countries that borders onto Bhutan? Come on. Because I do lots of oral examinations, all right, as people in the front row here know. So anybody tell me 2 countries that border onto Bhutan? 1 country. Aha, so international is a word. It's, pardon? India. India is one, China's another, that's right. It's up there in the Himalaya mountains. And for very obscure reasons, we have architecture that mimics what you can find there. So the talk title is Science, Research and Success on the Border. And then I added a source of excellence and creativity, because the students that I have had work with me have been outstanding young gentlemen and ladies and have exhibited hard work, diligence, creativity, and I will also say love. Love for working in a research group, love for the subject, and love for the experience that they had once they've left. When they're there, they sometimes get tension because it's hard work, but in the end, it works out very well. So, this is El Paso at the top. Who's been to El Paso, Texas? Not as many as I thought, but it's a big city, 800,000 population. I don't know how far it is because I flew, but I would think it's about 450 miles or something like that. I was wrong, 600. You know, Laredo is tucked into this part, which is a long way from everywhere. It really is, because it's about a 2-hour flight almost from Dallas. And yes, so it's a long way. But anyway, that is El Paso. That is indeed the Bhutanese architecture. This actually is cheating. It actually comes from Bhutan. It's a Bhutanese prayer temple that was given by the people of Bhutan to the people of the United States and was stuck up on the mall in DC for, I think, 2 years. It turns out that there's some law that says you cannot have something on the mall that isn't put there by the US government for longer than 2 years, and it has to be moved. And when it came time to move, the Bhutanese government said, El Paso, Texas. That's where it is. And we got quite a few international students from there. Some even do chemistry. I do annual retreats up in the mountains, and I have this tremendous urge to try and take a retreat to this particular place in the mountains, which actually is Bhutan, right? But I don't think that's ever going to happen. Okay, where do I come from? Anybody know where this is? I'm from England originally, so where is this?
Wimbledon.
Wimbledon, that's right. So this is where I grew up, just around the corner from the tennis club. I don't actually play tennis very well. I went to the university in the northeast of England, Wimbledon, southwest London. I moved way, way away because I wanted to remove myself from my parents. That's a straightforward statement, and I went as far away as I could within England, and that was 260 miles. That's it. You can't get further away, which of course in this society is just literally around the corner, right? But that's where I went. I lived in this room in the castle, that one. That was my room. The castle was built in 1068. I think that's when they started it. Took them 200 or 300 years to complete, but that's what I did. Then I moved for all sorts of reasons. I studied in England, got a bachelor's of chemistry, and started a PhD program in nuclear chemistry. Nuclear chemistry, what were they trying to do? They were trying to discover a new element. That is big, long-term research, and teams of 20, 30, 40, and I realized that wasn't my interest. I wanted something which was a little bit more immediate, where I could go into the laboratory, be creative, and walk out at the end of a month and say, hey, I made this new molecule. It's interesting or it isn't, but I wanted something more rapid. That's perhaps a fault of mine. I need to get results. If I don't get results, I think I'm probably not doing something as creative and useful as I would like. There's arguments on both sides of that, because some of the best science, people slave away for 2 generations. I mean, like the people that helped put the man on the moon. They've been studying in their laboratories at NASA and other locations for years. But that wasn't something that I didn't want to do. So after Toronto, I got a PhD. And of course, everybody from Europe who studies anywhere wants to come and do a postdoc. I went to the University of Georgia. That's where I learned about American football. I didn't particularly like it then. I don't like it now. I think if American football could all be over in 1.5 hours, like an English football match, then I'd be watching it. But it goes on and on and on, and then on and on. And it's tedious, all right? And there's all the timeouts. I mean, it doesn't appeal to me. So I'm at the right place in El Paso where we got a football team that I don't have to watch, all right? And after that, I went back and took a faculty position in England. I thought that was my career, all right? You can't read it, but on there it says, University of Sussex, we value your comments, but we don't have to listen. It's not exactly their motto, but that's what it's there for. And I thought that's rather amusing. Why did I leave? I left because of economic reasons. I want to tell you this because it's true. I had a family, 3 children, and the salary that I was receiving as a faculty member in England was low. I'd got more money as a postdoctoral fellow here at the University of Georgia, funded, I must say, by the Air Force. And I realized that if I was going to stay in England, I was constantly going to be counting my pennies, my shillings, my pounds, whereas if I said to my wife, let's just hoof off somewhere. So I thought, where can I go and still do what I wanted, basic scientific research in chemistry, but that the reward would be commensurate with my expectation. Whether my expectation was ethical, appropriate, I don't want to go into because it's my decision and for my family. But so we moved. And immediately there's 3 places, Canada, America, and Australia. That's what Englishmen look out when they see the world. Somehow Europe gets overlooked. We can come to that over a drink about Brexit. but Australia, New Zealand, Canada, and the United States. And the first one, my wife and I agreed, whoever gives you the first offer, take it. And it was the University of Texas at El Paso. The chair of chemistry was a fellow called Bill Whalen, and he went out on a limb. He hired me without any form of interview, didn't even tell the rest of the faculty until I'd agreed to go. It was a totally different era. But he's happy. Well, he's dead now, but he was happy when he was alive, and I'm very happy too. Okay, so now, international university. Science is international, okay? You know that, or if you don't, you will do by the end, all right? Because I'm going to repeat this over and over again. And I gave a talk to some students today, and there was a flag in the room. I forget the name of the room, but it was next to the library. Lovely little room. I liked it very much, with flags and journals. And there was one flag from India, and I asked the young lady, what flag is that? And quick as a lick, she said India. So I'm going to do this experiment right now. Let's try an easy one first. At least I think it's easy. This one, that's white, blue, red. Anybody? Yep. Who said that? Yeah, that's a Russian flag. All right, so that's well done. That was quick. Okay. And keep your cell phones and tablets off, because I'm going to ask this on a regular basis throughout the talk. We'll go to a different flag each time. Okay, now, who knows what this picture is? Just raise your hand. One, anybody else? I know your president probably knows it, but anybody else? This is a very famous painting. Okay, so could you tell us, please?
Yes, Picasso.
I'm sorry?
Picasso.
It's Picasso, and it's called the Demoiselles d'Avignon. It's the young ladies of Avignon. And it's a classic in art because of the following. If you look carefully, you can see on the left center, the faces of these ladies looks pretty normal. All right? He started out with a traditional, slightly cubist idea, but then he moved across, and by the time he'd finished, all the faces were African mask-like things. And this just threw the art world into sort of contortions. This was unheard of, right? The human form had been dealt with as a human form, but not played with. And he had this capacity to begin to see that there are other ways of looking at the faces, and you go from there to there, and it's quite self-evident. So this was a classic. It stands in the art world as an important moment in history. Well, we have the same thing in chemistry. I only teach one class at the University of Texas at El Paso, and that is all about the periodic table of the elements. All right? It's a wonderful, creative homage, in fact, to creativity over the years. It started with alchemists, and it just went from there. And so in 1869, I think it was, Mendeleev came up with his rudimentary form of the periodic table. And it's this that drives my insatiable, almost, desire to create new molecules. All right? I just like to create molecules that haven't been made, and therefore, what can you do when you've made them? You look at their chemistry. Is there something entertaining and interesting in that chemistry? So that's what I'm going to talk about. And I'm going to focus on actually one particular group, 4. And you can see these pretty colors. I've never really thought about this before. So group 4 and 5 are the only 2 vertical columns where you've got more than 2 colors. All right? And the colors represent something by whoever made this table. It wasn't me. I filched it off the internet. Okay? Carbon, clearly, I think you can call this a non-metal. Silicon and germanium, Ge, germanium, Si, silicon, these are what we call metalloids. They have characteristics similar to metals and non-metals, depending upon temperature. The transistor is all based upon silicon. Conductivity is a function of temperature. And then we get to the bottom, these 2, tin and lead, unambiguously in the world at large, metals. So this group, really entertaining, and that's where I spend a lot of my time. Actually, quite often combining these elements with metals over here, but I'm not going to talk about that today. So I'll just add one thing. In this journey for creating molecules, this is how far I've got in the periodic table. We have published or got a manuscript ready for that number of elements. I want to finish off my career. I think I've got some clever ideas about what to do with gallium and indium. Thallium I'll leave alone. It's a toxic, nasty material used for rat poison, and I wouldn't want to have it running around in my laboratory any more than I want a rat running around in my laboratory. And maybe over here, but I'm not totally sure about the rare earth, the alkali earths. But all the rest we've published on. So now then, I'm going to concentrate on tin. So that's the group, carbon, silicon, germanium, and tin and lead, that I'm going to focus on. And why tin? Well, that's a good question. It's widely used. It's a biblical element. There aren't many elements that you can go to the Bible and read about an element. Tin is one of them, okay? I can't remember the exact quotation. A long time since I really studied assiduously the Bible, but it's in there, and I know it's an old, ancient metal. So that's good. Does it have any uses? It does. There's a few of them. First of all, you all know that your toothpaste is full of stannous fluoride, all right? There are reasons for it. It's just a way to get the fluorine there, actually. I remember as a student in England, people were saying that in America they were beginning to put fluorine in the water. And there was an uproar in all sorts of locations in America because they said this was a communist trick to adulterate your water, because I wasn't here then, where in fact fluorine is very good. And now it's understood that most people around the world like fluorine in their water because it keeps your teeth going beyond what would have been a natural age without this treatment. Because we don't brush and floss enough, I'm told. I don't floss at all, much to the chagrin of my wife. She just thinks that's pig-like behavior. Okay, so what else? They're used in agrochemicals. It's used in rice growing to kill something called rice blast. I don't know what this is, but they use the tin. It's a fungicide. It's got some biological uses, and we're going to come on to that in a moment. Anti-fouling agent simply means that if you coat the bottom of your boat or ship with paints or materials that have organotins, that's a tin now with carbon bonded to it, you will find that this is very effective at stopping the build-up of mollusks and snails and all these bits and pieces that in fact slow down the capacity of that boat to move through the water. There was a story, I was at the beginning of the Gulf War. I think were there two Gulf Wars? I forget. Anyway, the Gulf War, all right? They had an aircraft carrier steaming around the Indian Ocean. And then the word comes, turn around, go back to the Middle East, all right? So they do what they're told. That's the great virtue of the American military. They don't make up their own minds. It's a civilian-run operation. They turned around and headed for the Gulf. But then they realized they couldn't go fast enough to actually have an aeroplane take off from the deck. They just couldn't. And the whole point of having an aircraft carrier is in order for airplanes to take off and land. They couldn't go fast enough because the hull was full of this sorts of stuff that had to be removed. And so they had to turn it around again and send it back to Honolulu or somewhere for cleaning. Well, if you think about that from an economic point of view, all these boats that come from China and Japan with all the goods that we buy from over there, right? It costs money. It costs a tremendous amount of money. And it's got a 40% increase in fuel consumption after 6 months at sea. That's how often you've got to clean the bottom. But if you've got paints that in fact don't allow for the bacterial, the barnacle, etc. growth, then this is a use of tin. It was. We've been able to find now that there's better ways to do it, less poor for the environment, but I'll come to that soon. So, what are we going to do? Oh, this is the other great use of tin. Only in America, the concept of a non-toxic bullet. You're supposed to laugh at that because this, to me, is ludicrous, all right? A non-toxic bullet. What they're really referring to is that most bullets have lead. And when you go out and shoot elk and deer and javelina and all those things, the bullets reside somewhere, and the lead leaches out. And so, therefore, the tin industry thought they were being very clever, that we will no longer have lead bullets, we'll have tin bullets. So comes the idea of a non-toxic bullet. Well, the Englishman in me finds that hilarious, okay? So, now, we're back before I get into something, we've got another question. Who knows, let's choose another one. This one. Looks very much, no it doesn't. This one. Yeah? No? Somewhere in Europe? Czech Republic. Who said that? Well done. That's very good. Most people don't get that. All right? And I have to look through these earlier to make sure I could remember where they all came from. So that's perfect. Okay. So this is carbon. Now we're getting into a little bit of science. Carbon is, under most circumstances that everyone is familiar with, is tetrahedral. If you take diamond, diamond is simply a network, three-dimensional, of carbon atoms bonded in a tetrahedral manner to form a perfect structural arrangement of six-membered rings. Very stable, very hard, highly prized by people because it's beautiful when you cut a diamond properly. Okay? So it's based upon a tetrahedral structure, and the reason that it's called tetrahedral is because if you join the apexes to this, you get the tetrahedral structure. So you might imagine that tin, which is in the same group, would exhibit the same structural units. And to a large extent, it does. But there's something about tin that I can now tell you without explaining why, because that's not what you're here for. You're just going to get an overview. Tin is what we call, in the business, a Lewis acid. A Lewis acid means that it's a species which can accept another pair of electrons as a donor. So even though its valence is saturated like carbons with 4 valence electrons to form an octet of valence electrons, it can accept more, all right? And so what does that mean? It means, for example, that this molecule that I put up here, so aryl means it's a substituted benzene. That's the 6-membered ring. There's a tertiary butyl group on the end. There's your tin. I should have made this colored. There's 2 methyl groups, CH3, and there's a chlorine. And when you look at the structure like that, it looks tetrahedral. But when you sort of stand back and look at it in its environment, what we call, well, it doesn't matter what we call it, we look back at it, you can see it's different. It actually is a polymeric material. That the chlorine that's on one tin, we'll take this one, that's the tin, methyl, methyl, there's the aromatic ring. That chlorine interacts with the next tin. This is acting, the chlorine's got a lone pair of electrons, and that lone pair of electrons can donate to the central tin to get now an incredibly interesting polymeric structural unit. That's background. This is in the literature. It's not something I did, it's something I knew, right? But tin can act then by interacting, even once it's got its regular valence structure, in a way carbon cannot. This you wouldn't see for carbon. You can have all sorts of groups attached to carbon. You're never going to find it in a trigonal bipyramidal or 5 coordination. That's the first point. Second point is tin is very active against all sorts of bacteria. And this is just to illustrate the fact that there's a lot of work by a lot of people to show this so-called Goldilocks effect. All right, what do I mean by that? This is the number of carbon atoms in a chain associated with a triorganotin chlorine. So here it will be 1. So, okay, 2, 3, 4, 5, 8. And I'm just going to look at this particular group here. On the vertical scale is something called the minimal critical something concentration, where the bacteria cannot grow. All right? And you can see for 1 carbon, 8 carbons or 7, very high concentration. But when you get to 2, 3, 4, and 5, or 2, 3, and 4, down here, 3, 4, and 5, very, very low concentrations. It's very toxic. These organotin compounds, with the right formulation of just about 4 carbons, are toxic. They're bad for us, too. They completely foul up your natural killer cell activity, and I'll come to that in a minute. So this is background. This was known. But I had an idea. This was, I don't know when it was. I'll say 15, 16 years ago. A proposal to the National Institutes of Health. I simply made a point. I first of all told them that organotin compounds are in the blood of most healthy Americans. It's there. 80% of the people living in Michigan have significant quantities of organotins. I don't want to go from why and where it comes from. And furthermore, that those organotins can stop the functioning of natural killer cells to, for example, kill cancer cells. This is in the literature, not by me, but that's understood. And so when you put that in the first 2 sentences of a proposal to NIH, and then say, this is pretty bad, but I've got a solution, then people wake up. They may not agree with your solution, but they're going to say, has he got the background to be able to fulfill an investigation into this area that might be useful? Our idea was as follows. You always needed a chlorine atom on the tin to make them bioactive. If I've got 4 organic groups on the tin, there's no bioactivity whatsoever. You need a chlorine. Chlorine is, I heard somebody today having to be told what electronegativity is. It's a very electronegative element, sucks electrons away from tin, which means it can interact better with other pairs of electrons. And so the idea that we thought was, well, look, the first step here is that the chlorine will ionize or partially ionize to give positive or partially positive charge. If I had a dangling arm with a sulfur, that I suggested that this would interact with the tin in such a format so that it'd swing around, interact, and that would make it totally unavailable for interacting with biological molecules like cysteine, histidines, or whatever. It's a simple, simple idea. Whether it would stop the interaction or simply change the selectivity so that the tin could interact with this species but not that. That was the idea. And so we had to, first of all, make the compounds. Okay, so I'm not going to show you how we made them. I'm just going to show you some results that we obtained. We made compounds like this. So here's the tin, carbon, 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 sulfur. Or it can be tin, sulfur, carbon, carbon, sulfur, whatever. 5-membered rings, the potential for 5-membered rings. These weren't known. We suggested that was going to happen. So we made them. And this was the work of Terry and Paula. And so let's just look very quickly at this and then just the numbers. This is a structure with tin in the middle. This is a phenyl group, substituted benzene. That's a phenyl group. That's a phenyl group. So 3 phenyl groups, phenyl 3. SNLL is the ligand I just mentioned. Here's the tin, carbon, aromatic group, and then in the ortho position, a methyl thiol. So there's sulfur. There's the tin. And you can see, even though they're not close, the sulfur is bending towards that tin. It knows it's there. And I talk about molecules like they've got personalities. They do. It's just for us to understand them and modify their behavior. Rather like children. I've got 5 children, so I can say that. Okay? So the distance between the sulfur and the tin in this compound, with just 3 phenyl groups, is 3.7 angstroms. You don't have to worry what that means. It's about the sum of the van der Waals radii. Okay? You put 1 chlorine on, and all of a sudden there's a dramatic, and this is dramatic, change in that sulfur-tin interaction. Goes from 3.7 to 3.45. This is a significant reduction. And if I take off 2 phenyl groups and replace them with 2 chlorines, see, it goes even low, very, very low. This is something like 70% of the sum of the van der Waals radii. That's just how close 2 atoms can get without bonding, all right? So this is way under there. This is a bond. This is real. And it turns out, we've done a lot of studies, it's not just in the solid state, but it's in solution, which means when you have a medication or you put into a bio-oriented aqueous system with cells, it's going to maintain this type of structural arrangement. So this was the first thing, and we published this, is now 11, 12 years ago. But that was the beginning. It was proof of structure, literally, that we could make these molecules and the structure would have strong interactions between sulfur and tin. So the question is then, well, that's good. So what comes next? Well, before we go on to what comes next, I want to talk about these 2 people, because the real reason I'm here talking about this is because of all the bad press that this border region gets from the government of the United States, telling us that we're infested with people of Latin origin, that we're an invasion. I'm simply here to show you how much rubbish that is. Okay, so I'll start with Paula. She grew up in Ciudad Juarez. They're both citizens of the United States. They were born in the US but lived in Mexico. She went to all the schools, in particular this one, Preparatoria Chamizal, which is, as you'll see, replete with an enormous amount of talent. And a lot of them come, for whatever reason, accidental and work in my laboratory. So Paula came as an undergraduate. She then studied and got also her PhD from the University of Texas, El Paso, in my group, studying these tin compounds, their structures, and other aspects of them. And she published quite a few papers of the work that she did, collaborating with people from Canada, Willie Lee, India, Ramesh Kapoor, and then other people from the region. Wonderful woman. And she is now the senior quality control person in a pharmaceutical company in El Paso, Texas. Absolutely, if I had a company to start and I'm looking around, who do I know that I want to hire and work for me? She would be number 1. She'd be in charge. I'd be in charge, but only because I don't know anything. She would be the person that has the integrity, the ethics, the hard work, and the intellectual acumen. She's delightful. Not that the other lady isn't. Teresita is just also a tremendous asset. She's just creative, hardworking, and she had perhaps one of the most difficult parts of this research to do, and that is to learn how to do what we call solid-state NMR. You have solution NMR here. Solid state is very difficult. Walking on the ground here, as I'm doing up and down now, is pretty trivial. But you try to do that on a planet with no gravity, but it isn't easy. You've got bloody great big boots on, and it's going to be very difficult. It's the same thing, solid-state NMR and solution. She solved the problem on how to prove that in the solid state and solution, the structures were the same. She also published a slew of papers. She was a graduate student in my group. First of all, she came from Our Lady of the Lake. She grew up in El Paso. And you can see the papers that she published also in this area. She is currently back at Our Lady of the Lake. It's a dream job. She's chair of chemistry, And maybe one day she'll be a dean, and then after being a dean, what comes next? Provost, and after provost, president. All right? She's that type of a lady. She's the chair of the local ACS section in San Antonio. She's special, very, very special. Okay, time for another flag. Let's get serious. Oh, come on. This one. Yes?
Kuwait.
Pardon?
Kuwait.
Kuwait. That's pretty damn close. I don't think it's Kuwait.
Jordan.
No. United Arab Emirates. All right? I had a very talented young undergraduate student, Zainab, who came from the United Arab Emirates. So far you guys are getting close, but we have to put that one down as a B minus. But, however. So, now, then Tanya came along. We had a point to prove. It was an important point to prove before we got on with the project, and that is, does it matter where that, what I call a dangling arm is, right? I've got a sulfur at the end of a dangling arm, and I want it to interact with the brain of the molecule, the tin, right? So you would argue that if I put the dangling arm on my foot, the odds are it wouldn't be able to interact with my head. So if we put this sulfur in a slightly different position, did it prove that we were doing what I said we were doing? Okay? Well, first of all, she made this compound, which is similar, from a simple piece of chemistry. Took this particular starting material, it's orthomethoxybenzyl chloride, reacted with metallic tin, and it gives this compound. 2 halides on tin, 2 organic groups. You can see again, just as in the previous case, the MEO group is still in the ortho position as it was before, and you can see to have 2 of them now makes the tin octahedral. It takes 6 positions around tin. So this should be extremely unreactive if we're right. We'll find out. But I said to Tanya, perhaps if you put this methoxy group here in this position or that, where it can't sort of interact with your brain of the molecule, the tin, we'll get a different sort of arrangement. And sure enough, Alejandro Meta from Cuernavaca is our staff crystallographer. He came all the way up from Cuernavaca to work permanently now in our institution in charge of X-ray facility. And you could see a very different structure, right? There's no intramolecular interaction between the oxygen or the sulfur, which is this. This actually is oxygen. But you see, when you put it in a different position, it's no way for this to interact with the tin that's going to be here. Unless it was with 2 molecules together, we thought this was possible. The oxygen of one molecule with the tin of another, like the tin chloride I showed you at the beginning. But no, it doesn't do that at all. It just dangles literally unreactive at the top or the bottom. Now there's the same motif that you saw for trimethyl tin chloride. The chlorine is acting as a base, and you get this nice polymeric material. Very nice. She proved the point that was needed to be proven. Yasmin was in the lab at the same time. She took these materials just to find out how did they interact with different cell lines. And for the life of me, I can't tell you I remember what the cell line was, because this was with a colleague of mine in biology. You know who it is? Who? Yeah, Renato Aguilera, all right? Yeah, he was here last year, all right. I hope he didn't talk about this, but it doesn't matter if he did, right? But the point is, all I'm going to say about this is it's an excuse to have the photograph of Yasmin, because she's another of these young ladies that's worked in the tin arena, and because this type of diagram here, where you're looking at the rupture of cells, tells you that the process by which the cells are dying, and it was a cancer line of some description, but I can't remember what, is what they call apoptotic. That is, that it's not a toxic effect of the tin just killing whatever it sees. No, it's modifying the biochemistry within the cell so that you get what is, well, I call it suicide. I'm sure the biologists have got a better word for it, but it's planned suicide. It's a way that you can see that it's not just that this stuff is toxic and kills everything, it's manipulating internal pathways. And that's absolutely crucial. So, okay, we'll just, Tanya, she went away after, she also came from Ciudad Juarez, got a bachelor's degree, then went on UCLA, got a master's degree, and then a PhD in chemistry. She's a postdoc, University of Wisconsin, in bio-oriented chemistry. Her PhD was in inorganic chemistry. And then after that, she became a safety officer, which is an interesting career choice for people. Someone was asking me, what do you do when you've got a degree in science? I would tell you, given the nervousness of society with chemistry, biological systems, safety officers are a career that's going to be more and more needed, all right? These are people who go around laboratories, find out how the process is working, how can you make it safer, and how can you stop the public worrying? Because the public tends to worry. I was telling some people earlier, the chemistry department at UT El Paso is in a brand spanking new building, and I must say your new building looks delightful. But ours has been up there for about 6 years. We still don't have it all. Lots of it is shelled because the state hasn't got the money to put stuff in it, but they've got enough to build it. But one of the things that's interesting is a previous dean, Michael Eastman to be precise, as a temporary dean, thought it would be a good idea to have chemistry in the same building as what? Computer science. Because he said, more and more chemists are getting more and more interested in modeling, so let's put computer science, and they can talk. Yeah, it was a ludicrous idea when he came up with it. It's even worse now, because computer scientists are chemophobic to the extreme. We have a Starbucks in this building on the second floor, very nice, but chemists will go down in their regalia, their lab coats. There'll be stains, right? What's the point of a lab coat if it doesn't protect you, right? And so there'll be all these stains, and then what happens? All the computer scientists get absolute, there's chemicals. No, don't let them come into Starbucks dressed like that. So there has to be a dress code. And you can't come in with an NMR tube because that's got chemicals in it. It's been a total bloody disaster, okay? Yeah, well, anyway, so the bottom line is it's been an entertainment. But she has just landed a plum job out here at the waste isolation plant in Carlsbad, New Mexico. That's where they store a lot of nuclear waste. And she earns now more than almost all the professors in the Department of Chemistry and Biology, and is very happy. Her husband actually works in El Paso as a safety officer for a big refining company. So they got a problem of commuting, but they'll find a way. Helicopters or something. They own that much. And then Yasmin, she went away. She got her bachelor's degree with us. She comes from also the Chamizal, same school, high school in Juarez, and then went on to the UT Southwestern, down there for a PhD in bioanalytical chemistry, then to the University of San Francisco, where she's got a full-time job doing programs rather like the one that I do, the MARC program, trying to encourage underrepresented groups to go into the field of science and scientific research. And her husband also. She just had one paper with me. No, she didn't. She had two. I'm sorry, Yasmin. She had two papers, and Tanya had one. They all publish from the group. This is the stimulation that you get from doing the work, that if it's interesting enough, you know that if you can just tease out the data, you can get a paper. And when you do that, you can go home to your mother, your father, your brothers, especially brothers, and say, hey, look what I did, all right? Or the other way around if it's a sister. So the point being, there's a tremendous pride in being able to say that you have contributed to the scientific literature. Okay, what comes next? Oh, another flag. Let's go easy on this one. Actually, let's try this one. Who's that? Hey, you're good. You don't answer anymore, okay? Let me shake your hand. How come you know that so quickly?
I love to.
Oh, you like flags?
Yeah.
Okay, good. Well, let's ask another one then. I'm going to test you. If you've got Peru, this one. Okay, it's Ukraine, which used to be part of Russia. It used to be called the breadbasket of Russia. Now it's a separate independent country. Okay, but anyway, congratulations. So then I had, more recently, Gabriela Vargas. She came as a postdoctoral fellow. That is, she already had a PhD from her university in Morelos, in the state of Morelos in Mexico, Cuernavaca to be precise. And she came in, and now we wanted to sort of change, not the thrust of the work, but we had one, I didn't like phenyl groups. These phenyl groups that you saw in the previous structure, which in this ortho position, they're very rigid. I thought, hey, look, more flexibility might be interesting. So she was able to make this compound here. Not going to go through the process, but here, so she made this compound, all right? And it's similar to the others because the sulfur is going to find the tin and bond to it, just like it did in the aryl systems. But there's a bigger flexibility because now you're dealing with sp3 systems. And so she made this molecule, and then Paco, who was then our crystallographer, because this work was done some time ago, he came from the University of Guanajuato in Mexico. Who's been to Guanajuato? Yes, it's my second home. People ask me, where am I going to go when I retire? And I said, well, I'm going to spend my time in 3 locations. One, somewhere in England, from place to place, sometime in El Paso, Texas, and then 3 months in Guanajuato. It's absolutely an idyllic city. It's the head of the university is there, the head of the government of the state of Guanajuato is there. It's got everything going for it. And every October they have a 3-week festival, Festival Cervantino, where music, theater, dance, it's heaven for someone like me. Okay, so there's the structure, okay? There's the structure. And you can see it does exactly what we had hoped it would do, but better because there's 2 of them. And so then, this is wonderful, thank you. So 2 chlorines and 2 of these. Here's a chlorine, there's a chlorine, there's the carbon chain, so it's a propyl chain, 3 carbons, and then the methylthiol opposite one chlorine, same thing, opposite the other. 6 coordination. We thought this is the one that we really want to try because it's got the same number of carbon atoms as the dibutyl tin dichloride, which is used everywhere and is found to be absolutely, totally toxic with respect to people. But here I'm modifying it by just inserting a sulfur. So carbon 1, 2, 3, 4, sticking a sulfur in. Can we really be that cute in chemistry? Just one Achilles heel in this molecule to stop it being so toxic and being useful? The answer is yes. Okay, so now we come on to its use. On the left is Fabiola, who was the undergraduate at the time, did the research. And here is Margaret Whalen, who is a collaborator at Tennessee State University. She studies natural killer cells. Now, I've got to be honest, I had no clue, and really I don't have much now, what is a natural killer cell, all right? I said, well, why don't you just, grow a lot of them in the laboratory. And they all thought this is just so funny. All these cells come from volunteers, all right? This is the sort of like a T cell or something like that. It's the immunology of your body, okay? These are key features. So what does Margaret do? Margaret has a wonderful setup, and I'm not going to go through it, but I could because it involves chromium. But she says, look, we can take molecules and we can find how effective they are at fouling up the behavior of natural killer cells, which of course is rather important. You cannot think of a medication for this disease if it's killing your immune system, right? You want to have something that's pretty good. So here we go. This is a control. So when you take, and I've forgotten what it's a 24-hour experience, 0.5 micromolar in organotin compounds with a certain number of natural killer cells. I forget the number. I should have put it there. Mea culpa. But anyway, just regular, with no treatment, the natural killer cells will basically lyse 80% of the cancer cells. This is the norm in this type of an experiment. In your body, you would like it to be a lot more. But when you do this outside the body, then you'll find that that's the norm. So the natural killer cells have not been treated. If, on the other hand, you let them bathe in some butyl tin chloride, dibutyl tin dichloride, the stuff that is all over the place, I'm afraid to say, then you can see that under the same conditions, just less than 20% of the cancer cells get gobbled up, deactivated, lysed by the natural killer cell. You do not want this material anywhere close to your immune system into your body. And yet it's there. You can go to the literature, okay? You put that shouldn't be phenyl, that should be pentyl. This is another deliberate mistake. That's 4 carbon atoms, this is 5. And you can see, 30% only. But with our compound, now, with an experimental error, and I've chosen the worst set of data, the worst, it's the same as not being treated at all with tin. So this molecule, this bis-methylthiopropyl tin dichloride, under the conditions that normally we would want to use, very low micromolar, it has no impact on the behavior of our immune system. That is important. It's more than important. It's worth saying, hooray, okay? We found something that, in fact, because of the dangling arms, stops the behavior with this particular biological system. Okay? I've got to show Fabiola. She went to this same high school in Juarez, Chamizal. I don't know, she just came into my lab by accident, but it was wonderful. She got a Bachelor's of Science, then she went down to the MD Anderson Hospital for her PhD in experimental therapeutics, translational research. She was in the lab with the samples from patients doing the work right there to find out what would be effective. Very exciting research. She then went to the FDA, and right now she is an investigator that goes around the world from time to time, certainly around the country, investigating places where they make drugs for North America. She's the woman that goes down with the team, but she's now got her own team where you go investigate what are the facilities, what are their practices. This is an important job for the federal government, and she's another one of these young ladies that grew up in Ciudad Juarez. And she published 3 papers with me as an undergraduate, and then also a bunch more down at MD Anderson. But I'm not putting them all up. I just want to have the imprint of my interaction with these people. Okay. Now this is time for a bit of humor. Can you read for me what it says here? Remember? Yeah, please, out loud. Ninth, that's what 1X means. Go on, carry on.
International Conference on the coordination and organometallic chemistry of geranium.
Okay. You were reading it so carefully and so slowly, I knew you'd read it correctly. 90% of the people that I ask, because I show this slide a lot, will say, because they know I'm interested in germanium, they will say, the organometallic and coordination chemistry of germanium, tin, and lead. But you read it correctly. This tells me that you pay attention. So, well done. But around the world, most people say germanium because that's what they expect. All right? So, it allowed me to publish this paper. This is a paper in the literature, okay, which simply says, I've made a new material, geranium, tin, and lead, synthesis of a novel material. And I love this paper. No one cites it because it's a joke, except that it is indeed in the literature. And I thank these people for giving me that opportunity. Okay, one last flag. Keep quiet. This one? Anybody? Not quite, close. Next door neighbor? Iran, right, okay. Iraq is this one over here, all right? Different colors too, but I mean, but again, it's not bad, you're getting in the area. So the international part of the institution is at least bearing some fruit, okay? Now, I'll go through this quickly because I think I'm spending far too much time. But never mind, it's interesting. I say it's interesting, and I'm going to fill in one of these forms at the end to evaluate the presentation. Okay, so that's fine. What am I talking about? Who knows what leishmaniasis is? Okay, it's a disease which is very prevalent where the colors are the darkest. So, sorry. Okay, here we go. All over Brazil, except Chile down there, okay? Certainly, to a certain extent, in Mexico and the lower countries of Central America, North Africa. It's sort of interesting that this is wet and damp, and this is dry and hot, but that's where you find a lot of it. That country there, anybody? Now we see a real map. Well, what's that country? India. So what's next to it? I think that's Pakistan or Afghanistan. That maybe not so good. Anyway, so this disease is carried by sandflies, and it's disgusting. My student that's working on this has all sorts of slides which I refuse to show. It just shows the skin erupting. It's disgusting. But it's a disease for a large number of people. And so we surmised from various clues in the literature that our compound might be useful. So, first of all, it's a perfect catalytic system. The sandfly starts it off. It's got these little what are called promastigotes in its gut. It then sucks blood from you. The promastigotes come into us. They go to mastigotes, which now have mobility. They go all over your body, right? Whereas the promastigotes don't. They just stick where they are. But as soon as they get into a good host cell in our body, they change. And then another sandfly comes along, has a drink of the milk, gets some of these, and then it changes back. And so the cycle goes on and on. Promastigote, mastigote, promastigote, mastigote. It keeps on going around. Catalysis for the chemists. It's wonderful. There's no catalytic format that I know that's as effective. How do we stop it? Okay, so this is the end. First of all, the work was done in collaboration with Dr. Rosa Maldonado. She's from Venezuela. I don't have her flag up yet because we haven't got the paper out there in the literature yet, but it'll be another flag. And then Itzel Tejeda, another young lady from Juarez, another young lady from the same school, the Preparatoria Chavizal. Absolutely amazing. And I didn't realize this when I put the talk together. I knew they came from Mexico. I didn't know they all came from the same school over a 10, 15-year period. Rather special. Okay, so what did she do? First of all, she took the promastigotes. That's the thing that's in the sandfly, right? It's not in us, all right? And she showed that all of these organotin compounds, diphenyl tin dichloride, dioctyl tin dichloride, dibutyl tin dichloride. Remember that first slide I showed where the activity is really strong for 4 carbons, 5 carbons? Well, look at the tin. The dibutyl tin kills these little fellas with incredibly low micromolar amounts. Our compound is still pretty good, right? It gets down to about 0.5, and when you get to this level, it's done its job on the promastigotes. But of course, that's not what we're after. We don't want to treat the sandflies, right? Okay, I give a hoot whether a sandfly has got these or not. I care about the people. So here then, we see the other part of this story, okay? We will now look at the cytotoxicity of our material for really what are healthy cells. I think these come from monkeys. I should know this, but I'm not the bio person. It doesn't matter where they come from. They're the ones we're going to infect with the promastigotes and amastigotes. And you can see that now you've got to get up to approximately, our compound is this one, all right? We've got to get up to this level, like 10 micromolar, far more than this, 50 times, 80 times more than that, all right? So, first of all, we know that this, as we've seen before with the natural killer cells, our molecule does not impact the effectiveness of the natural killer cells. It also does not affect the healthy cells that we're going to infect. So that's the good news to begin with. And it has to be done, because if these compounds fouled up regular cells, why bother? So this are the 4 pictures. This is, and I don't know if this shows up well, these are the healthy macrophages or the healthy cells before we've infected them, okay? This is untreated, infected, and if you look closely, you'll see lots of little blue dots. That's all of the little amastigotes that are in the cells, up to 100 in these things. What's the current treatment? It's this molecule. I can't tell you the structure because I've forgotten. It's amphotericin B, which my wife's a nurse, was a nurse, and she said in the business they call that amphoterrible. It's a disgusting drug that has so many bad effects on the patients, but you can see it's not even that effective because it's killed a lot of the whole cells, right? These are the infected ones. It's blasted most of them away, all right? And it also blasts away healthy cells, although it's used. I mean, this is a drug of choice. However, our molecule, this is a beautiful illustration. You can see now that they're healthy. The actual cell itself is just as good as it was. In fact, it even looks to me like it's better, but I'm not allowed to say that, all right? And the nucleus is still there, but you don't see any of the amastigotes in there. And it has what we call a selectivity index of 800. That is, it's 800 times more effective. Now, let me back off. What does that mean? It means if you take the concentration that you need to kill the host cell, and then the concentration that you need to kill the invading species, the amastigote, in the cell, the ratio is 800. That is phenomenal. So they are very excited about this, as am I, because we think that this might be a useful tool in the fight against this horrible disease. Okay, so that's the end of my talk, except to point out that at the beginning, I said this is a talk by Keith Pannell, as a professor of chemistry and biochemistry and material science and engineering and past president of the Texas, all that guff, right? The reality is that this is work by these ladies, all right? Teresita, whose mother and father were born in Ciudad Juarez, but she was born in El Paso. Well, they were all born in El Paso. That's how they become citizens. But they all lived and went to school on the other side of the border. This is a story of immigration, excellence, scientific acumen, of which these young ladies, or they're not young anymore, some of them have got careers, are very proud. I am particularly proud. And I use this, and I talked about this in Japan. I gave an after-dinner speech. Why did I give this talk? It was twofold. One was about the periodic table, which was obvious. The other was because when you go abroad representing the United States, and people think I'm a US citizen, and I am, they immediately start talking politics, and I'm up for it. I think politics is an important part of who we are, where we are, and the discussions about it are important. And it usually gets to policy like immigration, where our government has some really Neanderthal concepts of what is appropriate, how they define the people coming across the border, how they look for solutions to that problem, and how those solutions have resulted in the massacre of 22 people in El Paso, Texas, simply because the idiot that did it thought they looked like Mexicans. They probably did, for all I know, but the point is, that is crass. And I give this talk to point out to people around the world that, hey, that's just not the real story. Think about this as the concept of immigration and creativity and science. It's important. And then I finish up by pointing out people in the audience that I know. I've known these people for 30-odd years. And I say, hey, you're from Austria. What's happening in Austria? They have the same. What's happening in Germany? Just yesterday, a very right-wing organization in Germany became the leading party in that area. England, France, Poland, Hungary. This movement is all over. Scientists have a responsibility. Science is international, as we've seen, all those flags, people that worked with me from all around the world. Scientists are taken at face value with great respect around the world. Rightly so, because we try to maintain our integrity by just going after what we can prove in our own scientific realm of things. And it's time for scientists to start talking about what they see is happening and pointing out demagoguery wherever you see it and thuggism wherever you see it. I didn't know whether I'd get to this point in talking about it and if it is inappropriate to the president or your institution, but like I told the group in Japan, some of them didn't want me to get up and say things like this, but I said, yeah, just, you gotta, the expression in America would be suck it up. It's just, I needed to do it, and I do, and I will continue to do it. It's important. But the bottom line to this is those young ladies, and professor now, chair of chemistry at Our Lady of the Lake, in charge of the quality control at a drug company in El Paso, one of the biggest. They make these things that you put on your arm. If you go for an injection or a vaccine, you know, before they stick the needle in, pull it out, put on a Band-Aid. By the time the Band-Aid went on, if there was any infections around, you had it, all right? Now what they do, it's just simple, but they make oodles of money. They put on a Band-Aid to begin with some antibiotic material in it, then put the injection in your arm, and then pull it out. So it's so much safer. So that's what Paula does. Tanya is going to be in charge of safety at the waste isolation pilot plant. Couldn't be a more responsible job in the country if you really think about that. In charge of safety at a nuclear depository. Phenomenal. Fabiola going around the world investigating companies that want to make drugs for the market in North America. Pretty important job for this country, I think you'd agree. What else? Yasmin doing what I do, but at the University of California, San Francisco, trying to encourage young people to go into science, and Itzel hasn't decided what she wants to do. I have a feeling she's going to land up doing an MD, PhD, or whatever the equivalent is, veterinary science. That's what she seems to want to do, and I say good luck. These are the people that did the work. I just get out here and talk. That's the easiest part of the whole thing. But I've talked for long enough so that I'm not going to be at all afraid when your president says, Keith, would you like a drink? I'm going to say, oh, why not? Anyway, thank you very much.
We have time for a couple of questions. If anybody has a question? Come on.
Somebody must have a question.
Well, let's thank Dr. Pamela again.
Oh, no, dear. Okay.
Please don't forget to sign out. In your program, we also have the other speakers that are coming. Our next one will be November 9th, and she's going to be talking about Generation Debt and Do-It-Yourself University. So have a good evening.
And on this form, right at the bottom, it says 3. What would you like to learn about in future? Write down periodic table. And I'd like to come back. Oh, the International Year, that's right. It's too-